Hi, welcome to my talk on artificial intelligence. Should we remove the I? Actually, the title should be, maybe we should, and maybe it really doesn't matter. So this is going to be just, we're going to dive into more details on how these large language models work, like ChatGPT. And to examine the question, is it intelligent and does it really matter? Now, I'm not going to go much into the use of these wonderful chatbot tools, but into the mechanics. So anyways, I've been associated with programming for years, for about 40, and have got really mesmerized by the resurgence in AI in the last 3 or 4 years. Now, so now, all the images that I use here have been generated with ChatGPT. And when I started, we had these racks of these huge mainframes that would fill multiple floors. In fact, my first one filled two, and now we get that same or more power in an Apple Watch. The outline I think I've described. I'm diving into how these things work, and then we're going to look at some problems with calling it intelligent, and we're going to look at some neocortex-based solutions. What's AI? Well, AI is the capacity of computers to simulate human intelligence, and that key word is intelligence. So I guess we have to define what that means, and it's hard to encapsulate in a single definition, because like according to Jeff Hawkins, who is the author of Thousand Brains, how a brain made of simple cells, neurons, creates intelligence is a profoundly interesting question and remains a mystery. But one just I guess one definition, it's the ability of a system to learn and model the world, and the so yeah, the what's world. We all have different world models. We have we you and I we our senses taking information, and we create this model in our brain of on that world model, and it's different for everybody. And we have general intelligence. We are born with extremely little knowledge about the world, but we are born with the ability to learn very efficiently and to adapt in the face of things we've never seen before. In other words, we can connect new dots using the stored information we have at that point in time. This will become important later on. And with AI, the holy grail is this thing called artificial general intelligence, and this would replicate what that definition is. And the question is, can we evolve to the state of the art from narrow AI, which we now have, to AGI? In other words, are we going to evolve to the state where a company only has two employees? One is dog, the other is a human, and the job of the human is to feed the dog, and the job of the dog is to keep the human away from the machines. There are different components of AI. We're specifically diving into machine learning. What is machine learning? It focuses on using data and algorithms to simulate human learning and make decisions. But the key is we're going to learn without being programmed, which is totally different from the way I spent the last 35, 40 years, where we had to tell the darn computer everything in every little step. So the idea the computer is going to identify patterns and relationships and trends in data and make predictions. And neural nets are a subset of machine language loosely inspired by the functioning of the human brain. And I say loosely because they're really, we'll see later, it really is almost an insult to the human neuron to call these things neurons. But they're capable of learning complex patterns. And then the foundational architecture for large language models, and we'll look at that soon. How do these things work? Well, let's take an example here, really simple. But this simple example, it holds true to even the biggest of our large language models. You're back in grade school, you're trying to decide if you should go to the playground with your friends. And is it sunny? We have three factors here. Is it sunny? Are your friends going? Are you done with your homework? And we're going to assign, if this is false, we're going to give it a 0. Remember, computers only can deal with numbers, mostly. And now if your friend's going, we give it 1, which is true. And if we're done with our homework, no. So it's a 0. Now, these are inputs into our so-called neuron here. And this is a summation function. And if this function, so we're going in, well, part of the input here, we're going to assign weights. And these are relative importance to these factors. So, and these will influence our decision. So we're going to give a 3 to it's sunny, 5 to our friends going, and 1 to our homework. Well, probably we'll have a talk with a kid who had those values. But anyway, so these inputs and their weights are going to be summed up. So 0 times 3, 1 times 5, and 0 times 1 equals 5. And of course, and we're going to assign a bias here, seeing the bias is arbitrary. It's simply so if our sum is less than 6, we're not going to go. Darn, we're not going to the playground. Well, maybe we should do our homework. Now, we can change the answer. And this is kind of the key to how we train these networks, is that if we change our friends, that the weight of our friends to a 7, then of course we're going to get a different sum here. And of course now we're going to have a 7, and this is greater than 6. So yay, we go to the playground. Of course, that's as simple as you can get, and completely unrealistic. However, it does show the idea, I think. And as we get these deep learning neural nets or large language models, then we have multiple hidden layers here, and we get emergent powers start to appear. Now, I'm going to, as I said, I'm going to dive into more deeply into 2 main areas here: the training and what are called transformers. And with training is the first stages of the training process is unsupervised. We go up there and we scan all of the data from websites around the world, particularly Wikipedia, and we pour it into what we call the model. The model is our repository for all this data, and at the first stage, it's nonsense, because there's only random patterns. Because remember, this thing is trying to find patterns, and it's completely untrained. So if we start to ask it questions, well, it comes back with nonsense. And the output from this is further refined. We start to refine it at huge cost by bringing in human contractors who play the role of both the user and the ideal chatbot, and train the model to have human-like conversations and better answers. Now, and its training is largely a process of adjusting the weights through high school calculus and cost functions. Now, we're going to take a look here at how Grant Sanderson is going to show us in more depth how this works. Grant does a wonderful job of explaining these things.
Is to introduce the idea of gradient descent, which underlies not only how neural networks learn, but how a lot of other machine learning works as well. Then after that, we're going to dig in a little more to how this particular network performs and what those hidden layers of neurons end up actually looking for. As a reminder, our goal here is the classic example of handwritten digit recognition, the hello world of neural networks. These digits are rendered on a 28 by 28 pixel grid, each pixel with some grayscale value between 0 and 1. Those are what determine the activations of 784 neurons in the input layer of the network. And then the activation for each neuron in the following layers is based on a weighted sum of all the activations in the previous layer plus some special number called a bias. Then you compose that sum with some other function, like the sigmoid squishification or a ReLU, the way that I walked through last video. In total, given the somewhat arbitrary choice of 2 hidden layers here with 16 neurons each, the network has about 13,000 weights and biases that we can adjust. And it's these values that determine what exactly the network, actually does. Then what we mean when we say that this network classifies a given digit is that the brightest of those 10 neurons in the final layer corresponds to that digit. And remember, the motivation that we had in mind here for the layered structure was that maybe the second layer could pick up on the edges, and the third layer might pick up on patterns like loops and lines, and the last one could just piece together those patterns to recognize digits. So here, we learn how the network learns. What we want is an algorithm where you can show this network a whole bunch of training data, which comes in the form of a bunch of different images of handwritten digits, along with labels for what they're supposed to be, and it'll adjust those 13,000 weights and biases so as to improve its performance on the training data. Hopefully, this layered structure will mean that what it learns generalizes to images beyond that training data. And the way we test that is that after you train the network, you show it more labeled data that it's never seen before, and you see how accurately it classifies those new images. Fortunately for us, and what makes this such a common example to start with, is that the good people behind the MNIST database have put together a collection of tens of thousands of handwritten digit images, each one labeled with the numbers that they're supposed to be. And as provocative as it is to describe a machine as learning, once you actually see how it works, it feels a lot less like some crazy sci-fi premise, and a lot more like, a calculus exercise. I mean, basically it comes down to finding the minimum of a certain function. Remember, conceptually, we're thinking of each neuron as being connected to all of the neurons in the previous layer, and the weights in the weighted sum defining its activation are kind of like the strengths of those connections. And the bias is some indication of whether that neuron tends to be active or inactive. And to start things off, we're just going to initialize all of those weights and biases totally randomly. Needless to say, this network is going to perform pretty horribly on a given training example, since it's just doing something random. For example, you feed in this image of a 3, and the output layer, it just looks like a mess. So what you do is you define a cost function, a way of telling the computer, no, bad computer, that output should have activations which are 0 for most neurons, but 1 for this neuron. What you gave me is utter trash. To say that a little more mathematically, what you do is add up the squares of the differences between each of those trash output activations and the value that you want them to have. And this is what we'll call the cost of a single training example. Notice, this sum is small when the network confidently classifies the image correctly, but it's large when the network seems like it doesn't really know what it's doing. So then what you do is consider the average cost over all of the tens of thousands of training examples at your disposal.
So I think Grant does a great job of explaining this visually. So back to our slides. So what we're doing, this is our machine learning system. You pour your data into this big pile of linear algebra and then collect the answers on the other side. And then what if the answers are wrong? You just stir the pile until it starts looking right. Well, it's not quite that simple. So anyways, this training with great cost and amazing amounts of GPU, um, and produces what are called large language models, which are a form of a neural net that are tailored for natural language. They're trained on billions of words. So instead of our simple little example or Grant's example with the image, with the numbers, they can generalize from data they're trained on. They're generative, they're huge, and they can engage in interesting conversation. And that's its power. It can trick you into believing that you're talking to a real person, and thus we get lured into thinking they are truly intelligent. Now, the next thing we want to look is a transformer. These things like ChatGPT and O1, they're actually a transformer neural net, and it's important to understand how these transformers work. Again, let's bounce back. Let's
American
listen
true
to
mole,
Grant.
1 mole of carbon dioxide, and take a biopsy of the mole. You and I know that the word mole has different meanings in each one of these, based on the context. But after the first step of a transformer, the one that breaks up the text and associates each token with a vector, the vector that's associated with mole would be the same in all 3 of these cases, because this initial token...
Now, these vectors are. This vector is just an array of values that give modify the meaning of mole. Thus, they give semantic meaning to mole. So, as he's saying, a mole can have different meanings. This is how we
Embedding is
quantify
effectively
that.
a lookup table with no reference to the context. It's only in the next step of the transformer that the surrounding embeddings have the chance to pass information into this one. The picture you might have in mind is that there are multiple distinct directions in this embedding space, encoding the multiple distinct meanings of the word mole, and that a well-trained attention block calculates what you need to add to the generic embedding to move it to one of these more specific directions as a function of the context. To take another example, this is American...
Part 2 from Grant.
More generally than just refining the meaning of a word, the attention block allows the model to move information encoded in one embedding to that of another, potentially ones that are quite far away, and potentially with information that's much richer than just a single word. What we saw in the last chapter was how, after all of the vectors flow through the network, including many different attention blocks, the computation that you perform to produce a prediction of the next token is entirely a function of the last vector in the sequence. So imagine, for example, that the text you input is most of an entire mystery novel, all the way up to a point near the end, which reads, "Therefore the murderer was." If the model's going to accurately predict the next word, that final vector in the sequence, which began its life simply embedding the word was, will have to have been updated by all of the attention blocks to represent much, much more than any individual word, somehow encoding all of the information from the full context window that's relevant to predicting the next word. More generally than just refining the meaning of a word.
So, especially when you look at the fact that we throw away all that matrix math, all that linear algebra is thrown away, except for the last word, the two. So, the last word is soaked in the meaning from all the other previous words, but only those to the left. This is a matrix meat grinder. It's brute force, complete brute force. So how do we do it? And for years, this AI's been was a lot of the algorithms haven't changed since the 1990s. However, what changed is that we have so much more compute power, and mostly thanks to NVIDIA and its GPUs, the graphics processing unit. GPU and the graphics part is key. What they've been doing graphics, NVIDIA's been doing graphics cards for 30 years. And what are these things? They're math processors. They're really, really good at doing math, and especially matrix math. And parallel computing, so they can do multiple tasks at the same time. And they run a thing called CUDA, which makes them so that you can let part of the logic run on a CPU and then forecast to our GPU. And NVIDIA, for its credit, yes, they became super valuable over one of the 2 or 3 most valuable tech companies in the world, because these guys recognized as early as 2015 the importance of AI. And of course, people like Elon are building these huge data centers with 100,000 GPU servers. Now, there is the transformer, of course, which we talked about, is key. And some people are moving this logic into an ASIC, which is an application-specific chip. But all this stuff is completely brute force. And the power requirements are monstrous. We've had a 10 billion increase in the power requirements for AI. And just for example, the human brain only consumes 20 to 30 watts because it's a sparse computing model, as it only activates what is needed at the moment for a given context. And for example, Microsoft is looking into, and I'm not sure if they still are, given what I'm going to talk about later, into buying into and revitalizing the 3 Mile Island nuclear plant. And to train many of these models, like the ChatGPTs, it's equivalent to consuming the energy used by New York and London. Now, but we may be hitting a wall here, because some people believe that scale is all we need. We just keep making these, adding more data, adding more GPU, and we'll get better answers, and it will seem more intelligence. However, there are people like Francois Chalet is questioning this, and what we need to do is we have to find ways to measure the performance. But this is tough, because the moment we have an exam like benchmarks, well, the model soon learns those exams, and it's like cheating on your final, seeing the answers. And so we get other authorities, and like Jan LeCun. Now, Jan is one of the founders of AI. The so-called godfathers, along with Jeffrey Hinton, and he has a contrary view to Hinton. Hinton seems to be convinced the world is going to end. Well, LeCun says no. These machines do not have human-level intelligence. They have to learn a model of how the world works, and through sensory input. It's like when you're a kid crawling around the floor, you bang into things and you learn. They also have to be able to remember what these models now do. They throw away everything, and they have to be able to reason and plan. Now we're going to see that this may be changing, and the current large language models have the intelligence of a cat. However, the very knowledgeable cat. And of course, these are Jan, and Jan, I forgot to mention, Jan is head of research for Meta, which formerly Facebook. Humans are different, and these guys argue, Francois and Jan argue, humans are different from today's AI, and we are. I hope we learn quickly and continuously, constantly updating our model of the world. And this is part of what intelligence is. AI must be fully trained before deployed. We do not have to undergo a lengthy and expensive training phase to learn something new. These guys have to be trained at great cost, and it's done like every year or two, because it just costs too much money. When we think of intelligence, from seeing to touching to hearing, conceptual thinking is created by a common neural algorithm. This is not true. So we are infinitely more flexible as we can easily learn new skills. An AI system can be trained to be humans in Go, but it has no idea what Go is, where we can take and transfer knowledge to different domains. And the question is, are we on the path to create truly intelligent machines, or because of this scaling problem, entering an AI winter? Maybe we need a new approach, because deep learning does not put us on the path to AGI. Now, I have to admit, there's been the last 6 months. I've been had to maybe reconsider this. The old models, O1 and O3 from our friends at OpenAI were released, and these are the so-called reasoning models, because they will use a chain of thought reasoning by default, as that to generate multiple paths of tokens for problems like STEM and coding. But so they generate these multiple paths, and so they're going to think step by step, much like we do when we're solving a more complicated problem or type 2 thinking. Um, Now, and they will, but the way that they do it is by generating multiple answers, and then they're going to select the best answer through a majority voting. Now, does this work? Well, these models are different from the GPT models, and but they're using much more compute power and inference time. And inference time is when the answers are being provided. We've done a query, and it's going through and it's answering our question. But the question is, are they really reasoning, or just finding reasoning patterns in the training data? But they are impressive in their results. When we look here at the AIM math tests, they're scoring 83%. At the coding, 89%, and PhD level science questions, they're up to 78%. So impressive. So whatever they're doing, they're doing it well. Now, of course, it's hard to test these things because, as I said, they'll go out there. Any test you provide that is exam style, they're going to find the answers to, and they're going to put it into the model. So that people like Francois Chalet have their ARC test, and in their ARC it stands for Abstraction and Reasoning Corpus, for AGI. So it's, are we going on the path to AGI? Are we becoming more intelligent? And these tests are easy for humans, hard for AI. So if you look at, and here's a sample, and it's going to take input, and you're going to morph this into a new output pattern. It's showing you the pattern. So now if we have a new input here that looks like this, what's the output going to be? Yeah, you're going to have these color squares, ding, ding. So O3 scored 75%, where GPT-4 scored 5%. So a massive step forward, and it's looking, this isn't just another large language model, it's a leap in architecture and functionality. However, as I said, is it really reasoning? There is no autonomous learning. Human intelligence thrives on learning new concepts independently. O3 is not there. However, it's moving away. It seems to be moving away from that brute force, as it's about a smarter design and reasoning. And Francois reminds us O3 is a milestone, not the finish line. Now, all this talk. Now we're here. Okay, so where are we? We have these things that, well, they are mostly a meat grinder of matrix math, linear algebra, and they consume huge amount. We need huge amounts of money to fire at them. We have to have these data centers, that huge data centers. And of course, and the tech world loves it because we spend more money. NVIDIA stock goes up and up, and it's in the and AI is in the hands of about five major players: the Microsofts and the Open AIs and Google. However, along comes DeepSeek from China, blows everything out of the water. It's an open source Chinese model that was released in January 25. It shocked the world as was developed supposedly for 6 million, where OpenAI took at least 100 million. Well, we'll never be sure whether that's true, but it's highly optimized. But what they've done, remember, this thing is open source. So there's this really valuable. They're sharing this with the world. They're sharing their new methods with the world. And one thing they did do is they have a highly optimized transformer model. Remember that transformer, 57 times more powerful than what's in ChatGPT. And they can generate text 6 times as fast as OpenAI. Now, and these are just some performance. I guess this is not so clear here, but they are doing like 79% on the AIM test. So they're doing roughly comparable to what OpenAI does with their O1 models. However, okay, so this we may not need to consume all the CPU and my GPU, but regardless, don't get me wrong, these things are incredibly powerful tools, and they're tools that we should wrap our minds around. However, the future might be the intersection of neurophysiology and computers. Remembering that the brain, particularly the neocortex, is the organ of intelligence. Remember, biological neurons have little resemblance to artificial. In AI, the neuron takes all inputs and processes them, because the AI is based on an old view on how the brain works. Biological only look at a subset, and they use context to decide whether to fire or not. So the majority of the synaptic input doesn't make the neuron spike. It just makes it more ready to spike. It puts it into a predictive mode, which is what the brain likes. The brain likes to stay in a predictive state, and it's going to. And if the prediction is not true, then it's going to change its world model. Its world model is going to change, of course, which is different from how AI works. And dendrites will look like this with the neurons look like this with our dendrites, and then we have along here we do have our complex computational devices, which are almost like a mini large language model. A lot of processing power. Now, there's one more video I'm going to share with you. We have time, I think,
understands the world and creates intelligence is one of the most important questions of all time. If we want to know ourselves, and if we want to create intelligent machines, we need to first understand how the brain works. This language, arts, and science. It learns a model of the world in your head. The model recreates the structure of everything you know. Everything you do and experience is based on this model. Intelligence is the ability to create this model of the world. But how can a bunch of cells create a model of the world and everything in it? The thousand brains theory answers this question with a surprising insight. Consider a coffee cup. Neuroscientists used to think there was only one model of the cup. Since we can recognize the cup by touching it or seeing it, the inputs from the eyes and skin would connect to the single model of the cup But when we look at the neocortex, it is composed of about 150,000 units called cortical columns, each about the size of a grain of rice. We now believe that each column independently creates models based on what it's sensing. Therefore, there are thousands of models of the coffee cup distributed among thousands of columns. Some columns get inputs from different parts of the skin. They model what the cup feels like. And some columns get inputs from different parts of the eyes. They model what the cup looks like. But then why does the coffee cup seem like one thing, not thousands of separate things? Some of the cells in the neocortex send signals long distances. They're like wires that go from the left side to the right side, from the front to the back. What these connections do was not known. The thousand brains theory proposes that these connections allow the different models to talk to each other. In essence, they allow the different models to vote to reach a consensus, a singular perception of what we are sensing at any moment. We are not consciously aware of what's going on inside each column.
So, again, that's just Jeffrey Hawkins' idea. Now, but whatever, these are amazingly powerful tools, and they perform in just in the remainder of time here. Let's look at a few examples here. Here I have I'm inputting this image, and I'm asking him, what is this dish? And the answer comes back, it looks like Napa tofu, and which actually is true. And then I ask it for, and it shows all the ingredients. Then I showed it this image here. I actually feed in the image. I copy it right into ChatGPT, and I ask it, this is, I guess it's somebody's hand. And I said, what's wrong with it? And when you look right here, there is a broken bone with the foot. So the X-ray, so ChatGPT says it's an X-ray on the left foot, and the right arrow is pointing to what appears to be a fracture. And I actually asked, and I showed it a picture of an image of my supposedly my tooth that needed to be replaced, and I said no, it didn't. Now this chart here is I fit this into its relationship between these organisms, and I asked which organisms are the producers, and it gives me the right answer. So what it's doing, it's reading this, it's reading the image and making sense of it. And finally, I have this in some language, I think it's Spanish, and again, just make it bigger. You lucky Spanish speakers know the answer. I don't, but ChatGPT does. So it shows me my translation. And the other example here is where I think is really valuable is I can almost use it as my tutor here. And what I want to do here is I asked it, when was the fall of Constantinople? And it shows me it was in 1453. And Mehmed the Conqueror. Well, I want to know more about Mehmed. And so I said, tell me more about Mehmed. And so it does, and born in 1432, became the Sultan at 12, really young. And now I asked him to tell me more about the siege of Constantinople. So it goes into some of the timeline and the forces and the Ottoman tactics, which were brilliant, and the technology they deployed, including the use of these large cannons, and the significance. And then I asked to tell me more about how the Christians got around the chain of the golden horn, which is one of the key parts in the in the siege, and it shows me the details. And then and then I was aware there was a relationship between Mehmed and the and Vlad the Impaler, or Count Dracula, and again more information. So I just used it and I do my research for this lecture. I used ChatGPT to tell me more about how it works. And for any corpus of knowledge, it's a beautiful tutorial, a beautiful tutor. Well, so anyways, thanks for listening.